So the good news is that this last problem that we did, the weak and strong equivalence point, this is probably the hardest thing that we do, not just in 163, but in the whole year of Gen Chem. Like hardest in terms of it's tedious, there's so much stuff to keep straight, it is really, really, really hard to do. The last type of calculation that we're going to do in this section, don't worry, it is significantly easier than what you've already been through. This is calculating the pH during the titration of a weak and strong acid and base. So it could either be a weak acid with a strong base or a weak base with a strong acid. And we're calculating this time not at the equivalence point. So either before the equivalence point or after the equivalence point at any time other than the equivalence point. So it's going to start out feeling like it's exactly the same as the last problem. The first thing that we're going to do is write the reaction between the acid and the base. We're using the exact same acid and base, acetic acid and hydroxide. So because this is a strong acid, we have a forward arrow, no equilibrium, CH3COO-, and our other product is H2O. And we're going to get ready for an ice table. And with titrations, these ice tables are always in moles all the time. So we have to then, just like the last problem, we have to calculate the initial moles of acetic acid. That comes from the molarity, 1.5 molar acetic acid. That's 1.5 moles per liter. And the problem tells us we have 245 milliliters, 0.245. So this will give us our initial moles. 0.3675. And then we are also calculating the initial moles of hydroxide. And this one, this time we have the volume and the molarity of the hydroxide. So it's going to be easier for us to do this. 0.8 moles per liter of hydroxide times 0.120 liters, 120 milliliters. And that is 0.096 moles. And initially, we don't have any products yet, so that's a 0. So that's step 2. Because the hydroxide is a strong base, the reaction goes to completion. That's why we have just the forward arrow, no equilibrium arrow. So that means we need to find the limiting reactant of our two reactants. So we're looking at both of our reactants and which one of them is limiting. And it could be either one. For this particular problem, our limiting reactant, the thing that we have the least of, is the hydroxide, the OH-. So for us, it's OH- because we only have 0.096 moles, and we'll use that to determine the C, the change row, because it's completely reacting. We're going to get rid of all of it. So minus X plus X, the 0.096 is the same all the way across that C row, and step 3 is done. Oh, and also we have to calculate the E. So we'll just do the math in every single column. 0.3675 minus 0.096. We have, at the end, we have 0.2715 moles of acetic acid. We have 0 right here. And we have 0.096 moles of acetate, CH3COO-. So now, this is where the problem is going to get a lot easier. Next thing that we're going to do is calculate the molarity of everything that we have in this E row. We're going to start with the CH3COOH. We have 0.2715 moles of CH3COOH. And don't forget that we are using the total volume, not just the volume of the acetic acid, but the total volume. Our total volume was 245 milliliters plus 120 milliliters. 245 plus 120 is 365. That's our total volume, 0.365 liters. So that molarity is 0.744. And then we also have to calculate the molarity of, what else do we have? We have to calculate the molarity of the acetate. That is 0.096 moles per, this, it's in the same solution, so it has the same volume, 0.365 liters. 0.096 divided by 0.365, that is 0.263 molar CH3COO minus. Okay, so now we're done with step 4. Now step 5, we are actually right now already ready to calculate the pH. So there's 2 possibilities here to calculate the pH. First possibility, do we have any strong base left over? So if we go up to our ice table, we find our strong base, do we have any left over? We do not. We ended with 0 of the strong base. But if we did have strong base left over, we would use that amount to calculate the pH of the solution. And that would be it. It would be done. We would be all done. So that would be very, very easy. If this was a weak base, strong acid problem, we would be asking the same type of question just for acid. So instead we would be saying, do you have any strong acid left over? And if so, we would use the molarity of that strong acid, H3O+, to calculate the pH of the solution. But we don't have any, so we can't do that. We can't do step 5. Instead, we have to move on to step 6. When you don't have any strong base or strong acid left over, then you'll calculate the pH using Henderson Hasselbach. And that's also very easy to use. pH equals pKa plus the log of the base concentration over the acid concentration. First thing we need to do is calculate the pKa. It's going to be the negative log of the Ka. The Ka is 1.8 times 10 to the minus 5. And then the next thing that we have to do is figure out of these two, which is the acid and which is the base. Remember, the acid has more hydrogen than the base. So CH3COOH is the acid because it has 4 hydrogens. Our base concentration is 0.263. Our acid concentration is 0.744. And see this, I told you this is so much easier than the last type of problem that we solved. And so our pH is 4.2